Hey everyone, welcome to this video for P8105, a course on data science. This is the first in a collection of 3 videos on linear models, an extremely useful framework, one of my favorite frameworks for analyzing data. This video is going to focus on how you fit models as part of a tidy workflow. I'm going to start by giving an introduction using slides, and after that I'll demonstrate the material using a screencast. Feel free to skip around to the parts of the video you find most useful. To get the most out of this, I encourage you to code along with me. Everything is available at p8105.com, and there are links in the description below. Awesome. Let's get started. All right, so I'm going to try to give the fastest overview of linear regression that I can, and then I'm going to spend a little bit of time talking about how we might implement linear regression in R, and in particular in R as part of a tidy workflow. It's been a while since we've seen this figure, but hopefully it's still familiar. We've talked about the process that goes into doing data science or doing some kind of a data analysis. And you start by importing data, then there's a step where you need to clean things up and do some data transformations. And we spent a fair bit of time talking about each of these elements, the import, the tidy, the transform, and even visualize. And this course as a whole is not really intended to talk about modeling. The idea for this is to try to get everything in the context of a tidy workflow, but not to give the particular skills that have to do with doing data analyses, the whole range of things that you might do for doing data analyses. Now that said, I feel like it would be a glaring omission to just not talk about any approach to modeling. And so what I'm going to do in this video and in the next couple of videos is talk about linear regression as one approach that you might use to modeling. You can do other things here. You can do statistical learning. You can do principal components. You can do t-tests. I don't really care. At least in the context of like making sure that everything is clear and reproducible. But again, like I am going to talk a little bit about linear regression, and then you should be able to communicate all of this effectively also. Now, the reason that I am picking linear regression as the modeling approach that we're going to spend a little bit of time talking about is because linear regression is just really my favorite. Like I use linear regression not for everything, but if I had to pick one statistical tool to use for the rest of my life and didn't get to use anything else, I would probably land on regression. And the reason is that it is extremely flexible in the sense that it covers simple stuff. You can do 1 and 2 sample t-tests set up as a regression if you want to. You can also do really complicated things like scatter plot smoothing and additive models and automated variable selection via penalization. And all of this really does fit nice and neatly within the context of a linear regression framework, as long as you're willing to sort of push that framework to its limits. And in case you're wondering, like, yes, I really do t-test using linear regression. I think it's just, gosh, it makes a lot more sense to me. You don't have to do that, but maybe someday. All right, so again, this isn't really a course that's focused on the full treatment, a semester-length introduction to linear regression. Instead, we're going to do like the 3-minute version of this. I'm hoping that you are sort of getting the skills, a lot of the interpretation, the understanding of where regression comes from and how you might use it and how you can sort of push it in different directions. I'm hoping that that's coming from some other part of your overall training, right? But in short, here's what we're going to be doing if we're talking about linear regression. We're going to say we have some data, you get an outcome, and then some number of predictors for every subject that you're interested in. So I is going from 1 to a total sample size of n, and we are assuming that the data are generated under the following model, where you have an intercept and then a regression coefficient out there in the world that tells you the effect of the of predictor 1 on the outcome. And you sort of write down all of those combinations of coefficients and predictors, and that tells you the structure of the regression that you're interested in. Now, of course, the outcome that you observe isn't just the combination of these coefficients and the predictors. There's always some error term that's floating around on top of that. And the assumption that you have to make is that those error terms have mean 0 and variance sigma squared. Often people will also assume that those errors are normally distributed. That is helpful in a lot of ways. It's a nice assumption to have, but you don't have to have it if you just want to do linear regression. If you are going to do linear regression, then you set all of this up and you say, well, what is the thing that I know and what don't I know? You know the outcome, you know the predictors. What you don't know are the regression coefficients. And so you estimate those regression coefficients using ordinary least squares. And this covers an awful lot of ground, and I guess I'm not really going into a lot of things yet. I will talk briefly about interpretation and hypothesis testing and other things. But again, this is intended to be a very fast introduction just so that we can sort of establish a framework for the notation that we're going to use and the terms that we're going to use and things like this. So in this linear regression framework, the outcome that you're going to be interested in is a continuous variable, and the predictors can be anything that you want. I really do strongly prefer the language of saying outcomes and predictors rather than independent and dependent variable, or maybe the reverse of that. I would get into the habit of that. I think if you're going to be talking about independence and a statistical framework, like that's, it's just maybe don't say that. So instead, what we're going to be talking about is outcomes and predictors, or outcomes and covariates, or things like this. In linear regression, we're going to be talking about continuous outcomes. The predictors can be any of the data types that we've talked about up to this point. So you can, for example, I think, have things like numeric variables. You can have categorical variables. And if you're willing to convert other things to either numeric or categorical, you can start getting things like binary variables. You can start getting date variables. You can start getting true and false variables, maybe coded as a category. Like these are all sorts of things that you can put into a linear regression. Now there is one complication, of course. If you have continuous predictors, you just put continuous predictors into your model. If you have categorical predictors, what you end up constructing are indicator variables. And again, my preferred language is an indicator variable, not a dummy variable. And the idea there is that you want something that indicates whether or not an observation is in a particular group. So you would have a reference group for your categorical variable, and then you would say for every non-reference group, is this in sort of non-reference category 1, yes or no? And that's going to be coded as 0 or 1. Is it in non-reference group category 2, and that's going to be coded as 0 and 1. And what you end up with that is a collection of 0, 1 variables that says, in short, you have a reference category and you want to make subsequent comparisons for non-reference group back to that reference category. And I'll show you what I mean by that in just a second. All right, so this is the sort of picture that comes up an awful lot when you start talking about regression. And you can tell from my handwriting, it's really better that I teach a class where you type code rather than you have to write things down. But I'm sort of assuming here that I've got a model with one continuous predictor age and one binary variable sex, and that sex variable is coded as 0 or 1. And it's going to be coded as 0 if subject I is female and 1 if subject I is male. And I'm sort of implying that default coding based on the way that R would treat this variable by default. If I had a sex variable that was coded as female and male, R would by default put that in alphabetical order and make female the reference category. And that's going to be something that's important to understand when you're thinking about how to do this in R. But suppose this is what we're interested in. I've got age, it's continuous. I've got sex is 0 or 1, 0 if the subject is female and 1 if the subject is male. And I'm going to talk very briefly about the interpretation of coefficients. I've sort of labeled a few things here. I've got one cloud of points in a regression line for male subjects and one cloud of points and line for female subjects. And when I talk about sort of the slope here, beta 1, or equivalently the slope here, beta 1, what I'm talking about is a specific interpretation. And the way that I always arrive at that interpretation is to say that beta 1, this is a magic trick, beta 1 here is equal to beta 0 plus beta 1 plus beta 2 minus beta 0 plus beta 2. And the reason that I like to do this formulation is that now this first collection of terms is something that I recognize from my model, and the second collection of terms is something that I recognize from my model as well. And in particular, this first collection of terms is the expected value of the outcome if I knew that the participant age was 1 and I knew the participant sex was male. Again, if the participant age is 1, I have a 1 here multiplied by beta 1. If I know the participant sex is male, then my indicator variable is set equal to 1 right here, and I end up with beta 0 plus beta 1 plus beta 2 if I know these covariate values. So again, I get an expected value for the response given a collection of predictors. And I can do that same sort of thing for this second term here, where now I'm saying age is equal to 0, plug in 0, sex is equal to male, plug in 1, and I get beta 0 plus beta 2. And if you just do this subtraction, you're left with beta 1. Great. Now, why is this helpful? It's helpful because now I can talk about this beta 1 as a difference in things that are related to my model. So I have a difference in expected values of y, a difference in the expected outcome given that age has gone from 0 to 1 and I have kept the sex set at male, right? And that's a little bit restrictive. It turns out that if I changed age to any number and then I put age here as that number minus 1, I would end up with the same thing. And I could, again, like code sex, instead of saying male, this could be female, and beta 2 would fall out in both of these. But you sort of end up in the same place. And so the very generic way of describing what beta 1 is the expected change in y for a 1-unit change in age, keeping sex and keeping anything else that's in my model fixed at some constant value. And so that's why here, when I'm looking at this, I can say if this is a 1-unit change in x, then my expected change in y is beta 1, and it doesn't really matter if that's on this male line or if that's on the female line. Doesn't matter. As long as I stay on the same line, I can do that 1-unit change in x tells me how much I expect y to change, keeping sex fixed. In a similar way, I haven't written out, but you can do the interpretation for beta 2. If you plug in any value for age here and any value for age here, but you change sex from male to female, you're going to get a beta 2 term on this side and no beta 2 term on this side. So beta 2 is going to be the difference in the expected value of y comparing males to females, keeping age fixed. And it doesn't matter if you're keeping age fixed at something like this or something like this. As long as this is your model, great, you've got your interpretation for beta 2. And I think that's, that's the way that I always think about these things, is to figure out how I can isolate a regression coefficient in terms of expected values, and expected values given particular collections of covariates. So great. Now we know how to interpret everything in linear models, and that's great. So the next thing that I'm going to mention is, if you are interested in understanding one of those regression coefficients and whether or not it is non-zero, the way that you're going to go about doing that is through this sort of a hypothesis test, where you construct a test statistic, follows a t-distribution, and for large samples it has a normal distribution, and your test statistic is whatever your estimate is minus whatever your null value is, and often that null value is 0, divided by the standard error of that estimate. So again, on the previous slide, if I said, it looks like beta 1 isn't equal to 0, you could test that by asking, given this collection of data, what is my estimate for beta 1, and what is the standard error of that estimate, and then take the ratio of those two things, and congratulations, we have a test statistic. Now, I've mentioned in passing the estimate for beta hat, or the estimate for the coefficients, is going to come from ordinary least squares. There are similar kinds of things that you can do to get standard errors out of these things. That is the subject for a different class. We're just going to say, if you get one of these things, well, that's great, and you can do a hypothesis test of the null hypothesis that your regression coefficient is equal to 0. And I'm not really going to get into it, but if you have multiple coefficients, and in particular, I think this is important, if you are putting a categorical predictor into a model and it induces, say, 3 indicator variables, well, if you want to test whether or not that thing is significant, it's not just that you're testing one coefficient at a time. You really want to test whether or not all of those indicator variables taken as a collection is a significant improvement on a model that doesn't include all of those predictors. And we're not going to write out all this stuff, but you can use an F-test to do that. Sometimes people will refer to doing this F-test as doing ANOVA. It's true, that's fine, that is what it is. But I sort of prefer to think about this in the context of doing an F-test rather than a T-test, okay? Or I guess doing an F-test as an extension of doing a t-test, rather than doing like a t-test over here and ANOVA over there. All right, so next big thing that's worth keeping in mind if you're going to be doing linear regression is that we have made a collection of assumptions when we wrote down that regression model. And a lot of those assumptions are things that you can check by looking at the residuals from your fit, where I'm thinking of residuals as the difference between your fitted value and the actual observed data point. Basically, what are all of those epsilon i's floating around? And the reason that this is helpful, or it's helpful to look at residuals, is because you have made some assumptions about these. You sort of assume that they are centered at 0. Often, you assume that they have a non-skewed distribution. They're sort of equally distributed in that way and that way. You can also identify outlying values. Outlying residuals turn out to be heavily influential on your estimated coefficients. And if you have outliers in your residuals, it's often worth double checking whether or not the model fit that you get, the model that you're reporting, is sensitive to those things. Oh, and I've just realized that I've put this question mark not outside of my parentheses, and I've recorded this video now. That's going to bother me, but listen, it's going on the internet. All right, so the next thing that you might want to do if you're looking at these residuals is not just the distribution of those residuals, is whether or not there's any structure in your residuals. And what I mean by that is, have you missed some obvious pattern? If you look at your residuals against the fitted values or your residuals against the predictor, have you fit a line when what you really needed to fit was a parabola? Have you missed like some skewed trend on one tail or on the other tail? Are there, when you look at these things, do you see that there's low variance on this side of your fit, but high variance on this side of your fit? Those are the kinds of questions that you want to ask when you start looking at your residuals, either at their distribution or how they compare to fitted values or to individual predictors, right? Because departures from these assumptions, I guess this is a point I want to be clear about, departures from these assumptions mean that a lot of these statistical things that you have done, the hypothesis tests that you have produced, and in some cases the interpretations that you're making, if your model assumptions aren't right, then those downstream things that you're doing are not right either. And you want to be really careful about that. So after fitting a regression model, you really do want to do a lot of these diagnostic checks. I am not going to go into, because it's a whole, gosh, you could spend a semester on linear regression by itself. Or at least a big chunk of a semester on linear regression by itself. You can also spend a lot of time on what are referred to as generalized linear models, where if you have an outcome that is 0 or 1, for example, that doesn't fit very nicely in the context of a linear model where you're assuming that things are continuous, your outcomes are continuous. And so in the case when you have something that is non-continuous, you end up in what is referred to as a generalized linear model. And it's just generalized because the right-hand side is still linear, but you are generalizing the left-hand side to account for continuous and binary and count and whatever other kinds of things you might have on the left-hand side. You're generalizing a framework that starts out the same over here, but then ends up very different on this side. And the thing that I've written down here is a logistic regression, where on the inside of this, I am looking at the odds that y equals 1 given a predictor x, the odds being the ratio of probability y equals 1 given my predictors over probability y equals 0 given my predictors. And then there's some logit transformation that takes whatever's on the inside of that and maps it to a whole straight line so that the right-hand side of this model still works. In cases like this, well, I guess logistic regression, I think, is after linear regression. I think it's one of the models that I use the most. The regression coefficients are interpretable. Beta 1, for example, is an odds ratio, and that turns out to be a really handy fact. And I will just sort of close this out by saying that generalized linear models, that counts as regression. That's still, if I'm picking like one tool and I'm picking linear models, like I get generalized linear models for free. That's part of it. Okay, so you're going to be fitting linear models in R, and that's sort of what we want to talk about now. There are two functions, generally speaking, that are going to cover a lot of ground. LM will do linear models. GLM will do generalized linear models. If you need other things, if you want additive models or you want automated variable selection or whatever else it's going to be, there are other functions that you might have to use aside from LM and GLM. The things that go into the LM function is first the formula that you're going to use. You want to tell it the outcome that you care about, and then tilde to say this is my outcome and everything on the right-hand side are predictors that I'm interested in. You're going to give it the list of predictors that you want to include. And you're also going to give it a data set that includes a variable y and an x1 and an x2, or some variable, hopefully with a clearer name than y, and then the names of the predictors that you're interested in as well. But you're going to give it both the formula and the data. For GLM, you also have to be careful to tell it whether or not you have a binary outcome or a count outcome or something like this. But still, you're mostly going to be giving it a formula and a data set. R was written long enough ago that the output of these things is complicated and also kind of a mess. linear models, there's just a lot of stuff that comes out of a linear model fit that you might be interested in, and that for a long time people have been interested in. And so it's great in some sense that the output is complex, because there's a lot of stuff that linear models do that you might want to have. But the problem with that is having a very complex, kind of messy output can make it difficult to do things in what is nonetheless a tidy framework. And so what has been developed over the last couple of years, there's a Broom, and I think there's now like a Broom extension where they're sort of splitting Broom into one or two different things. But the Broom package, generally speaking, says if you have the output of LM, that's great, and it's got a lot of stuff, but we can give you the pieces of this that you think are that you're probably most interested in, and we can organize that as a nicely structured data frame. And so I use Broom very often after fitting a linear model to get the results that I am most interested in right back into a data frame, so that I can sort of continue doing data frame kinds of things. Broom works for a lot of packages. It works for a lot of analyses that you might do. Covers an awful lot of stuff. And very often, like almost any analysis that I do, one of the first things that I try is like take the output of an analysis and try to tidy it up using Broom. And a lot of times that works, and I get the information that I care about. So that's sort of what our workflow is going to be. Define a data frame, fit a model, tidy the results, and then operate on those tidied results. And we're going to see how sort of all of this works in a big workflow. Okay, so let's do that in a screencast. Love regression. All right, we're gonna jump in here and start fitting some models. This is the usual kind of a framework. I've set up an R project for this collection of videos. It's called the Linear Models R project. I also went ahead and copied over basically my usual template R markdown file. That's going to be, we're talking specifically about linear regression here, so it's called Linear Models. I'm loading the tidyverse, and I'm also going to load P8105 datasets. That's going to be where we get the example data that we're interested in. And then I run the rest of this stuff to just sort of make sure my plots look right if I end up making plots. Now, the data set that we're going to be taking a look at is the NYC Airbnb data set that has showed up in a few of these videos in the past. And I'm going to do a couple of sort of standard data cleaning steps just to make our lives a little bit easier, make my life a little bit easier. The first thing, as usual, I'm recoding stars to be the variable review scores location divided by 2. That takes stars from like 0 to 10. To 0 to 5 on half-step increments, and the idea there is that we're getting the actual stars. The other thing that I'm doing, I'm going to rename neighborhood group to borough just because I find that easier to remember. We're going to be looking at Manhattan, Brooklyn, the Bronx, and Queens. I'm filtering out Staten Island. That's not because I have anything against Staten Island in particular. It is because in this example, we're going to be looking at a variety of regressions, and there are just few enough observations in Staten Island that I didn't want to be building regression models on something where there aren't a lot of observations. And then the other thing that I'm doing is renaming neighborhood to neighborhood. And the reason that I'm doing that is I'm getting rid of this U that always bothers me. I can never remember that spelling. So I'm changing it. All right. So I'm going to run all of this code, and let's start trying to fit some models as a result of this. So that's my import data. I'm going to fit a model. And the model that I'm going to fit, I guess even before this, what I'm going to be most interested in is the price of an Airbnb rental, and I want to know how that is related to the stars and the borough where this is. So what is the star rating that goes into this? And that's going to be a numeric predictor. And then what is the borough? And that's going to be a categorical predictor. And just to make sure that we're sort of all clear about this, I'm going to do NYC Airbnb. Let's just make a quick plot. And I said on the x-axis, I want stars. On the y-axis, I want price. And I'll do color equals borough. And then I'm going to do a geom point here. Right, so there's a lot of overlap here, but basically the idea is that I want to fit some line that runs through stars and that maybe is different for each borough, right? So we sort of talked in the slides that with a categorical predictor I can have sort of borough here and then a different borough above and maybe a different borough below as a categorical predictor, and I'm going to get parallel lines for each of those things. That's the model that I'm interested in fitting right now. And this is not a super great plot, but it does enough for me to understand roughly what I'm going to be interested in doing. So let's fit the model we care about. And the model that I am interested in fitting here is a linear model relating price to stars plus borough. And the data that I am using is NYC Airbnb. Okay, and I'm going to save this as something just called very generically fit. I'm only really going to be fitting one model or overriding this model as I do other things. And for now, I'm not using a great variable name here. I could call this Airbnb price fit. If I were going to fit a bunch of different models, I would want to differentiate in some way. But I'm not really worried about that. So for me, for now, fit is a good enough variable name because I'm not doing an awful lot. All right, so fit. Let's take a look at what we've done. We have, in fact, just fit a linear model. There's a lot that's happened here in the background, but we're not seeing an awful lot. So let's look at the results. And this is where it starts to get a little bit weird. It starts to get a little bit weird because if I look at, for example, just the fit object, it tells me the call and it tells me the coefficients. And if I look at a summary of this, which is one of the things that you might often do, you get a lot more information, right? So now you get like the call and something about the minimum residual, the median, the max residual up here at 9,000. You get coefficient estimates, which I'll talk a little bit more about in just a second. And then you also get things like residual standard error and degrees of freedom. We have the R squared and the adjusted R squared. We have the F statistic that talks about the overall goodness of fit and things like this. It spit out sort of a lot of stuff. And I could do, well, what about summary if all I wanted was the coefficients? You can do that. Can you just get the coefficients of the fit? Yep, you can do that too. Although now, summary of fit using a $ coefficient, and I'm doing that because like in base R, I don't have a lot of choice. That spits out something that looks like a table. It's not actually a data frame. It's just sort of like a formatted something. I don't think it's a data frame. I'm curious now that I've said that. It's a matrix. It is a formatted matrix, because of course it is. So you get a matrix, but if you just look at the coefficients, you get a vector without the standard errors or the p-values. And God, I mean, there's a lot of stuff going on here. You can do other things. If you don't want the coefficients, you can get, I think, the fitted values of the fit, and it spits out this super long vector of all of the fitted values. I think you can get the residuals too, residuals or resid. Is that going to work? Yeah, you get like a super long vector of the residuals. All right, so what I'm saying here is there has been some useful stuff that R has produced either in looking at this fit or in looking at some of these other outputs, but I don't hardly ever use any of these things. Let's look at the results better. What we're going to do instead is tidy up the results of this. We're going to use the Broom package, and the first thing that I'm going to use is glance of fit, and this just gives me real quickly some of the most relevant information. And when I say relevant information, I mean the most useful one-number summaries that come out of this. So I get the R squared and the adjusted R squared. I get the statistic and the p-value that goes along with the global test of whether or not this is significant. I get things like the log likelihood and AIC and BIC, and those things can be helpful when you're trying to do model comparisons. Again, we're not going to worry about that, but AIC and BIC come up as useful things every now and then. I get things like the degrees of freedom and the residual, the number of degrees of freedom for calculating a residual. I get the sigma or the residual standard deviation. So I'm getting some useful information here. And critically, this is formatted as a data frame. I have produced a tibble. What I use actually more often is Broom tidy, the fitted object. And what this is going to produce is, again, something that looks very much like that matrix that we saw a minute ago, but now it's structured as a data frame. So I want to talk through this real quickly. What I have here is a variable for term. There are 5 coefficients in my model. I've got an intercept and then a coefficient for stars. And then I have coefficients comparing Brooklyn to the reference group, Manhattan to the reference group, and Queens to the reference group. And what those are going to tell me is, in short, for a 1-unit increase in stars, I expect the price of the room to go up by $32, keeping the borough fixed. And then in the remaining, if I'm comparing Brooklyn to the reference group, and again, the reference group here sort of implicitly, I'll talk more about this in a second, but implicitly the reference group is the Bronx. What this says is for the same star rating, an Airbnb rental in Brooklyn is $40 more expensive than one in the Bronx. Manhattan is $90 more expensive than one in the Bronx, and Queens is $13 more expensive than one in the Bronx. Each of these estimated coefficients has a standard error, and if you do this minus 0 divided by the standard error, you get the test statistic, and you can do a hypothesis test using that test statistic and get a p-value. So here the p-value is 1.27 e to the minus 36. That is pretty clearly significant at a 0.05 threshold. Brooklyn and Manhattan's compared to the Bronx are also significant. Queens doesn't seem to be. And we're not going to talk an awful lot about statistical significance right now. I'm just pointing out, if that's the sort of thing that you're really interested in, that you can get p-values out of this, and you can even get p-values now from a nicely structured data frame. This is the sort of thing where often, if I am working on a report or I want to see something like this, this is the kind of thing that I generally do output. And I think one of the reasons that I keep emphasizing that this is a data frame is because I might be tempted to do something like this. Often, what people are going to be most interested in is the estimate and the p-value. You don't really need the standard error. So I'm going to select minus standard error and minus statistic. Let's take a look at that. And then I'm going to do something like tidying up these three variables, right? So when R has constructed the indicator variables that go along with the borough variable, it just appends the overall variable name with the level of that variable. So I'm getting borough Brooklyn, borough Manhattan, borough Queens. And that's maybe not the nicest way to do this. So I'm going to mutate, and let's say that term is equal to str replace. And I'm going to say anywhere I see borough, I want to replace that with capital borough and a colon and a space. Let's take a look here. That did not work. Oh, I need to tell it what am I replacing. In the term variable, replace borough with borough. All right, so that's a little bit cleaner. And you can even take this a step further if we're going to knit this and do knitter cable. And let's take a look at the results. Both knit this. And then, or sorry, run that code chunk, and now I'm going to knit and see what we're left with. So I've imported my data, all of this. Oh, I'm spitting out all of this out. Ooh, I need to not do that. So I'm actually, let's just say include equals false here, because I really don't want to print the entire vector of everything. All right, great. So this is better. I get, okay, I get the model fit here, a glance version of things, and then when I tidy up the output using broom tidy and export the result as a table, here it is exporting the result as a table. So that's all pretty nice. I might like change that a little bit more if I were being real careful and just say digits equals 2 or 3, because you don't really need all that level of detail. Okay, is everything making sense so far? I think so. All right, so what I'm going to do next is switch up a little bit and take a step back and think about the factor variable things that are sort of happening behind the scenes here. So when I say I'm going to take a look at like the factor variable things that are happening behind the scenes here, so be in control of factors. We have talked in the past in some of these videos about the choices that is happening right here. So I guess even before that, I'm going to print this out and I'm going to say in the NYC Airbnb dataset, the borough variable that I've used as a predictor and that I used in constructing this plot, the borough variable is a character variable. And we spent a lot of time saying that what happens if you are trying to use a character variable in some context is that very often that gets converted to a factor variable. And factor variables have both there's like a string label sitting on top of a numeric actual variable representation. And so what you get when you convert a character variable to a factor is you sort of preserve the text, but now you've added this structure of a 1, 2, 3, 4, 5 in the background. And if you're not careful about that, then R is going to do its best guess. R is going to make a choice, and it's going to say, all right, you know, you've given me this character, and I need a factor. I'm going to convert a character to a factor, and I'm going to assume that the 1, 2, 3, 4, 5 ought to be in alphabetical order. And so that's sort of happened in a couple of ways here. When I run this, and I get my plot, it's put these in order, although it's sort of, the order is only apparent from the legend here. It has put them in order according to the borough in alphabetical order. Bronx comes first, then Brooklyn, then Manhattan, then Queens. And when I fit my linear model, the same sort of a choice was happening here. So when I run this, I get Bronx as the reference group, always, and then I am comparing the remaining factors to that reference group. I'm comparing Brooklyn to the Bronx, Manhattan to the Bronx, and Queens to the Bronx. You can do some other things, though, if you really wanted to. So what if, for example, got to get a code chunk. What if, for example, I wanted to change to make the reference category for the variables that I am interested in, the reference category is just the most common one, right? In this case, you could maybe make an argument for something else, but I'm going to say there are a lot of Airbnb rentals here. I want my reference group to be the one that has the most Airbnb rentals. And I'll do a similar thing when I say, we'll look at room types in a couple of minutes. I want room type to be treated as a factor variable, not in alphabetical order, but treating the reference group as whichever one is most common. So I'm going to even just go ahead and overwrite my data set real quick. NYC Airbnb is, take that data set, NYC Airbnb, and mutate so that borough is a factor. And I'm going to put this factor in order of frequency of borough. And I'll do the same kind of thing with room type. Okay. And what I'm going to do next is first look at that plot again. And let me just copy and paste code. All right, so it's a very similar figure. What has changed is the ordering on this axis. And so the order of frequency is Manhattan has the most observations, Brooklyn has the next most, Queens has the next most, and Bronx has the next most. So now borough is in order of the frequency of these things. And if I refit my model, I'm just going to do room tidy on that fitted model. Now what I have is similar results, but using a different reference category for the categorical predictor that I'm interested in. So stars hasn't really changed. Again, stars is going to be whatever the change, whatever the expected change in Y for 1 unit change in stars, keeping borough fixed. It doesn't care. But Brooklyn now is being computed in reference to Manhattan rather than in reference to the Bronx. And so previously, I might not be able to scroll up and show it, but previously we had been comparing Brooklyn to the Bronx and Manhattan to the Bronx. Now we're comparing Brooklyn to Manhattan and the Bronx to Manhattan and so on. So there are, if you sort of ask, all right, well, if I took Brooklyn and compared it to this, and I took Manhattan and compared it to this, and then I wanted to compare Brooklyn to Manhattan, you could get a difference between these two things. And that is what you get here. It's giving you the same information. And if I looked at things like Broom glance, Broom glance on fit, the adjusted R squared, the AIC, all of this has stayed the same. I haven't changed my model in a fundamental way. I've just changed what is being treated as my reference group. And this is important. It matters because, when you want to start interpreting coefficients, it is important to make a comparison to a plausible reference group. But it doesn't, I guess the point I want to make here is that it hasn't substantially changed what is actually happening. All right, so the next thing that we're going to do, let me knit this. It's probably time to commit. It's definitely time to commit. All right, so what we're going to do is plot data, fit first model, look at factors. Wonderful. All right, so what we're going to do next is try to take a look at diagnostics. And when I talk about diagnostics, what I mean is things like fitted values, things like residuals, things like this, right? Now, one of the things that we have tried to do up to this point is to do something like the following. So we said, all right, if I take, what did I say? I can get residuals by doing like resid or residuals of my fit, and it's going to spit out this super long vector. And gosh, once I have a vector, I'm just really unhappy. I don't want to have these things floating around in my workspace. What I would like to be able to have is in the data frame that I started with, can I get all my variables and then like tack onto that the residuals that I'm interested in? Or can I get all of my variables and sort of tack onto that the fitted values that go along with these things? And the answer to that is, yeah, you absolutely can do that. So what we're going to do is take advantage of the modeler package. And you can sort of see it's got right at the very beginning some things that we're interested in, add predictions and add residuals. We're not going to worry about add predictors, but let's look at add residuals first. And it's asking for the data that I want to get the residuals for. My data is NYC Airbnb. And then it wants to know the model that I'm interested in. The model that I'm interested in is fit, not get. And so if I just print this out, what I'm left with is everything that looks almost exactly like my data frame. This is, in fact, exactly my data frame. I've got price, stars, borough, neighborhood, room type, and so on. But this has added a column for the residual values based on this fit. Okay, so I've got now, in my model, I have fit, and I've tried to understand how does price relate to stars and borough here. And I fit some model and I got some residuals, and this is saying this $99 is about $9.47 higher than my model would predict. This is $35 higher, $20 lower, $4 higher, or sorry, $4 lower, and so on, right? So I've got now the residuals based on my model fit. And what's sort of nice about this is that you can start to do things like looking at distributions of residuals, right? So I can take the residuals here and I can do like a ggplot where I want to have on the x-axis the borough and on the y-axis the residuals. And let's do a geom violin. Okay. So what I'm looking at here is the distribution of residuals in each of the boroughs, right? And what this is sort of showing, it's a little bit hard to see, but you've got a lot of the residuals are sort of evenly distributed right down here around 0, and same for Brooklyn and for Queens. The Bronx has sort of a narrower distribution here, but Manhattan, Brooklyn, Queens, and so on, those all have like really extremely high residuals somewhere up here, right? We're sort of looking at things where in my original data plot, you saw that nothing is really going to make good predictions about these. For Manhattan, this looks like it's colored for Brooklyn. There's one for Queens. These are always going to be really big outlying residuals, and that's what I'm seeing here. I get some really big outlying residuals for Manhattan, Brooklyn, and the Queens. Not as many for the Bronx. If you wanted to sort of double check here or sort of zoom in, I think we can use ylim. Let's do minus 500 to 1500. I think this works. So you can sort of zoom in and see, yeah, you know, even excluding those residuals, my distribution, excluding those outliers, my distribution of residuals here is really pretty skewed. And that's a problem in the concept of whether or not the linear regression that you're doing is the right thing, and whether or not the hypothesis test that you're doing are sort of the right thing. There are issues that come in because in this case we have done, we've got these big outliers. That's a problem in some sense. I'm not going to talk in this video about how you might go about fixing that problem. What I'm interested in more right now is to say, if you fit the model and you want to do these regression diagnostics, you want to understand whether or not there are issues in your data set, well, you can get to your residuals in a nice tidy structure. And I might even tidy this up a little bit more and do like NYC Airbnb, piped directly into modeler add residuals and tell it what fit you're interested in. And then we're just using ggplot to take a look at the residuals here. We're doing some really helpful regression diagnostics using mostly tools that have been available to us in the past. The next thing that we might do, I guess, you know, if we're doing this residual plot, I might do NYC Airbnb against predictors, not just against fitted values. So here, the distribution is telling me that there's some issue. I've got some skewness in my distribution of residuals, and that's one problem. And I'm going to go ahead, modeler, add residuals again from the model called fit. And I'm going to do ggplot where on my x-axis, I'm going to say x is stars and y is residuals again. So this is residuals against predictors. And I'm going to do geom point. And I guess I might even do color is burrow. You know what, I'm not going to do that. I'm going to facet against burrow, just to sort of see how this plays out in each of the burrows I'm interested in. I did, in fact, mean to use plus, and I meant to say facet wrap. Okay, so what I get here is, actually this is interesting, right? So what I'm seeing here is, in Manhattan, you really do have this problem of residuals getting wider distributions as you get to higher star values. When you get to 4 stars, 5 stars in Manhattan, that distribution of residuals has spread out quite a bit. And there are a lot more of these sort of really big outliers. That's where a lot of this skewness is coming from. And the same is true in Brooklyn, where the distribution of residuals gets quite a bit wider as you get farther over in the star count. Queens has one outlier, which is potentially interesting to take a look at, to say, what is it about this one observation in Queens where there is a $5,000 residual, right? This is clearly a differently priced observation in Queens than it is somewhere else. And if we wanted to, we could sort of here say, you know, filter based on residual being more than 5,000 and burrow equal to Queens. I'm not gonna though. If you're following along at home and you want to take 30 seconds to see what's going on, good for you. And then Bronx doesn't have these issues of spreading out in residuals. It's just not one of the things that come up. Now again, this is useful kind of exploratory diagnostics, looking into what's going on. I'm not talking about how exactly we might fix any of these things. I'm just saying this is something that you probably want to do when you're fitting models that look like this. All right, so that's maybe enough diagnostics for now. Let's do hypothesis tests. So in some sense, we have done a few hypothesis tests already. So if I take fit and I do room tidy the result of this, I am doing hypothesis tests, or R is doing in the background on my behalf, hypothesis tests on this estimate using this standard error, computing this statistic and this p-value. And all of that is based on doing a t-test for this coefficient. And you can also do t-tests for individual coefficients here. Is Brooklyn significant? Is Queens significant? Is Bronx significant? In comparison to the reference group of Manhattan. Are each of those differences statistically significant? What I'm going to say that you sometimes want to do, especially if you have a categorical predictor with multiple levels, is not ask whether individual levels differ from the reference group, but to ask whether this predictor as a whole, the categorical variable as a whole, is significant in the context of my model. So here I'm saying, you know, this does t-tests by default. But if you wanted to predict, or sorry, what about the significance of burrow? If you wanted to test everything in, all of the categories in here, you want to get a test of all 3 of those regression coefficients at the same time. Again, I'm not going to say like why this all makes sense. I hope you're learning about this somewhere else. What I'm going to do is an F-test or a NOVA. Either way you want to describe it works. And to do that, what you have to fit are 2 different things. A null model, which is going to be LM of price against stars. That's the model that works if my null hypothesis that burrow, is unassociated with price is true, then I'm not going to put it in my model. All of those coefficients are going to be 0. And I'm using data NYC Airbnb. My alternative model is a linear model of price against stars plus burrow, and the data is NYC Airbnb. Gosh, can't type. Airbnb, okay. And then to compare these two models, I'm just going to use this ANOVA thing, comparing fit null to fit alternative, and it's going to take care of what I need. So what this says is a couple of different things. I'm fitting two different models, and it's giving me sort of an ANOVA table here. It's giving me the F-test statistic, and it's giving me the p-value that goes along with that F-test statistic. I'm not going to worry about some of this other stuff. It does say that there are 3 degrees of freedom involved in this. There's sums of squares stuff like this floating around. I'm just going to cross my fingers and hope that I can tidy this up a bit and see. And yeah, I get like a tidier version of this where I can look at the statistic and the p-value, and the p-value is low enough that obviously there is some difference here. Now, again, I'm not really going to go into whether or not I think this is a good idea. Or I'm not, I guess even more than that, I'm not going to go into like when you ought to use an F-test and when you ought to use a T-test, and can you use an F-test first and then go look at individual T-tests. That's not really something that I'm going to talk about right now. Other than to say, if you do an F-test first and then you go and do a T-test second, you do have to worry about multiple comparisons at least a little bit. And if you have 2 categories or 3 categories, maybe that's not a super big concern. But if you're doing an F-test and you're asking whether or not you want to include 10 different things, then multiple comparisons, corrections, and understanding that the T-tests are, you're doing a lot of them like that, that gets to be a slightly more complicated problem. Okay, so I'm going to knit all of this. Okay, and let's commit everything before we start getting a little bit weird again. All right, so what did we do? This was Diagnostics and hypothesis tests. Great. All right, so what I'm going to do now is let's nest models, or nest data and fit models. Nest data, fit models. All right. So suppose one of the things that we were interested in here is whether there is an association between stars and price, and that association differs by borough, right? What I fit so far has said, well, I get one line that tells me the association between price and stars, and I keep that slope fixed and I move it up and down to go to one borough to the next. But I could have, maybe Manhattan has this slope and Bronx has this slope and Queens has this slope, right? Maybe I could get sort of different lines here. And I could also sort of throw into this room type. I could say like, well, what about room type? Does room type have a bigger effect in Manhattan than it does in Brooklyn? Or does room type have a bigger effect in Queens than it does in somewhere else? Now, there is a model-based approach for dealing with this, that if you wanted to start getting into this, one thing that we might try to do is fit what are called interactions, where you get sort of a slope on stars and then an interaction term between stars and borough, and the combination of those things give you some way to understand how stars affects price in this borough compared to this borough. And interactions are important. They're sort of complicated to understand. They are really important, and they're important for reasons that I'll talk about in just a second. First thing that I'm going to do, though, is actually fit one of these. So let's regress price on stars times borough. And I think maybe what I'll do is also put in there an interaction between room type and borough using data is NYC Airbnb. Now I'm calling this fit also, and then I'll do, room tidy fit and see what kind of thing we're getting out. Now we're getting a lot of stuff. So I get main effects and I get interactions. I know that overall stars has this effect. When I say overall, I'm sort of thinking in my reference category, this is the effect of stars. If I wanted to talk about the effect of stars in a different group, I would need to look at the combination of stars and the interaction between stars and borough. And if I wanted to look at the combination of room type, I can get if I wanted to say room type, I can get room type of private room and room type shared. That's going to tell me what's going on in my reference group of Manhattan. If I wanted to know what effect room type has in the Bronx, I would need to say, all right, what's going on with room type in my reference group? And then how does that change in the Bronx here and here? Now, I am seeing some things. So stars increasing does make a difference. It looks like maybe the impact of star on price seems lower in the other boroughs, and I'm sort of eyeballing this. The p-values don't look all that significant, so sort of heuristically, maybe it's a little bit less of a connection between stars and price in other boroughs, and it's sort of in the direction of, you know, Manhattan is a little bit more price sensitive there, but nothing super significant, so I wouldn't worry too much about that. It does look like room type, you know, sort of goes in the direction, again, my reference group is the most common, which is an entire apartment. Private rooms are less expensive by about $120 in Manhattan and by $154 in Manhattan. And those differences are smaller if I am looking in other boroughs. I want to sort of make sure I'm saying this correctly. So if I wanted to know what is the difference between a private room and an entire apartment in Brooklyn, well, I would take the overall effect and I'm going to add that to the effect, the interaction term in Brooklyn, and I'm going to get something like $90 instead of minus $124. Right? Like that's sort of the process here. Now, the reason, like you can sort of tell, you start getting interactions and keeping track of all of the different directions is not always easy. What's nice about having this framework of interactions is if you wanted to assess statistical significance, you could compare one fit that has interactions to another fit that doesn't have interactions and ask whether or not that is a significant improvement in your model. And I think it is important separately somewhere else in your life to think through how you use interactions and how you do testing in the context of interactions to understand whether or not something is an important contributor to your model fit. What I'm going to do instead is something that is much more exploratory. So this is pretty formal and also complicated. And what we're going to do instead is, this is more exploratory, but maybe easier to understand. What I'm going to do instead is, like, sort of what I'm interested in asking is like, well, what is the effect of stars in Manhattan, and what is the effect of stars in Brooklyn, and what is the effect of stars in Queens? And I can get to all of those things using this kind of an output, but what I'm going to do instead is just say, gosh, wouldn't it be great if I could fit one model for Manhattan and then I could fit a different model for Brooklyn and a different model for Queens, and I could just look at the star coefficients and try to understand whether or not something looks a little bit different. So what I'm going to do now is sort of build up a little bit from scratch. I'm going to start out and say, suppose I took my NYC Airbnb data set, and what I wanted to do was nest everything except for the borough. So I'm going to nest everything except for borough here, and just stop real quick and take a look at this. Not nest equals borough, nest everything except borough. So now what I've got is a tibble for boroughs, Bronx, Queens, Brooklyn, Manhattan, and then I've got an entire data frame that has price, stars, neighborhood, etc. Price, stars, room type, neighborhood, whatever you want. I've got 600 rows in the Bronx, I've got 3,000 rows here, I've got 16,000 rows in Brooklyn and 19,000 in Manhattan. And given this, given data sets in a list column, I love list columns, given data sets in a list columns, I could ask, is it possible to fit a model to this data set, and then fit a model to this data set, and fit a model to this one, and fit a model to this one? And the answer is yes, you can absolutely do that. And you can do that by using mutate and map. So I'm going to say that the models that I'm interested in, if I can map across entries in this data column, I'm going to map across entries, and what I want to fit is a linear model, and I'll just start out and say, let's say price against stars, and I'm going to be clear that my data argument here is my placeholder .x. Oops. So I've got, .x is the thing that I'm iterating across, and I am using a placeholder here to say that's where that argument needs to go, right? That's what I'm trying to do here. And I'm just going to run this again and make sure that this works. And it's giving me a column of now, it's a list column. List can store anything. So I've got a list column of linear model objects, and I'm just going to like double check what happens if I pull out the models column. And it's got me a list of 4 things, and this looks like what would happen if I fit a linear model for price against stars. I get intercepts and I get coefficients for each of these, and I've got 4 linear model fits in this list column, and I'm feeling pretty good about that so far. But now I'm gonna again, I'm like, if I don't really like the output of LM when I'm not doing this in a list column, I don't like it in the context of a list column either. So what I'm going to get is a results column by mapping across models, and the function that I'm going to map is broom tidy. And I could be sort of specific here and say, you know, .x is equal to model and tilde broom tidy of .x if I needed that placeholder. The reason that I'm not is that broom tidy knows that it's got one argument that it cares about, and it's going to be whatever you're putting in. LM is a little bit more complicated, where this argument that you care about is somewhere else in that function specification. So I'm using a different interface with map from one line to the next, but the process is the same. I'm in this line starting with the data set. I'm fitting a model to this data set, and then fitting a model to this one, and fitting a model to this one, and fitting a model here. And then given each of those models, and I'm at the end of that, I've got a new column for models. I am using broom tidy on the first entry in that row, the second one, the third one, and so on. So broom tidy is tidying up this, and then tidying this, and then tidying this, and then tidying this, and storing that as another list column. Oh my gosh, I'm so excited. I've got another list column, and tidy gives me a tibble, 2 rows and 5 columns, and we'll take a look at that, I think, right now also. So let me just sort of pull results and make sure I understand what's going on. So it's giving me that nice tidy output where I've got the intercept and stars for each of my 4 models that I fit. And now I'm sort of, this is why I like list columns. I don't really remember what 4 is, and I don't really remember what 3 is. So here, I guess 4 I can see now. 4 is Manhattan and 3 is Brooklyn, right? So I'm going to do just a little bit more. I'm going to come over here and select, let's get rid of data, and let's get rid of models, and then let's unnest the results. Okay, so now I'm sort of looking at a variety of things, and in fact, I'm gonna tidy this up even more. I guess once I unnested each of those sub data frames that stored results out of Broom, I now get the results for the Bronx, and I get the results for Queens, I get those for Brooklyn, and the data frames are now included over here. I get a term, an estimate, a standard error, and an intercept for the intercept, and for stars in the Bronx and Queens and Brooklyn and in Manhattan. And if I wanted to sort of, you know, I usually don't care about the intercept, so let me filter term equals stars. And so now what I see, again, in a very exploratory way, in Manhattan, there is a significant association between stars and price. And that association is like $43 increase for each 1 unit increase in stars. Brooklyn is less than that, and by the time you're over here at the Bronx, there's hardly any association between stars and price, and the p-value doesn't appear to be significant, right? Now again, I can't say for sure that any of these boroughs are different from Manhattan. I can't say anything about whether or not those are statistically significantly different from each other because I haven't fit this all in a joint model. I can do that if I fit an interaction term up here and I do some appropriate hypothesis testing. I can't do that here. So this is a little bit more exploratory, but maybe it's an interesting thing to take a look at. Now in this one up above, I did include sort of room types. Let me sort of take a look here at including room type. And I'm just going to say, let's get rid of term not equal to intercept and see what my results are. So this is, I mean, it's starting to get a little bit trickier. I could do, what else could I do? I could say, let's select borough, term, and estimate, and then let's make this easier to read but less tidy. Pivot, wider, names from borough, and values from estimate. I don't think these need to be in quotes now that I've typed it. And that's, I may have to debug this. Let's check. Oh, looks like it worked. All right, so what I'm looking at here is, what is the effect of stars in Bronx, Queens, Brooklyn, Manhattan? What is the effect of room type in each of these? Going from a entire apartment to a private room will save you about $50 in the Bronx, and it'll save you about $120 in Manhattan. Going from a shared room or an entire apartment to a shared room saves you about $90 in Queens and about $150 in Manhattan. Again, I'm not going through and doing like regression diagnostics on any of these individual fits, and I'm not asking whether or not these differences are actually significant, but as a quick way to sort of get an idea about what's going on, I think nesting data and then taking a look at the results turns out to be a pretty helpful thing. And in fact, let's make this a little bit maybe more challenging. So let's nest even more. So suppose I wanted to ask the same kinds of questions about room type and stars, and I wanted to take a look at that in the context of neighborhoods within Manhattan. All right, so here again, like what I'm going to try to do is fit a bunch of linear models for every single little neighborhood that I have in Manhattan. I've got quite a few neighborhoods in Manhattan. I want to know really what's going on here. So let's take the NYC Airbnb data set, and I'm only going to care about Manhattan. So borough is Manhattan. And I'm just going to double check that I understand what's going on here. I've got price, stars, borough, neighborhood, Battery Park City, and some other ones, and then room type. So let's nest everything. Data is everything except for neighborhood. And now what I've got is a similar data structure that I had before. I have a data frame with price, stars, and room type for Battery Park City, for Chinatown, for Chelsea, for Civic Center, for East Harlem, for East Village, and so on. I've got 32 of these neighborhoods in Manhattan. And then the thing that I want to do now is basically what I had done before. So I'm just going to, let me see if I can just start copy and pasting stuff. Let's just copy and paste up to here first. And I'll talk through what I'm doing now. So what I am doing now is for each of these data frames, I'm going to fit a model that relates price to stars and room type using this data frame and then this one and then this one. I'm going to get a separate model for each of the 32 neighborhoods in Manhattan, and then I'm going to tidy up all of those results, and I'm going to get rid of the intermediate things. I don't really need the data frames anymore. I don't really need the models either, and I'm going to take a look at the results that come out of this. And what I'm left with is things like, what is the impact of stars in Battery Park City? What is the impact of stars in Chinatown? That seems weird. It gets cheaper in Chinatown as the stars go up. You might want to look at that. Same in Chelsea. And then I can start doing things with this even, right? So what I'm going to do, let's sort of take a look at like the coefficient for room type. Suppose I wanted to understand what's going on with the coefficient for room type across all of these different things. So I'm going to get rid of everything that isn't room types. Let me filter str detect in term the structure room type. Check that this works. So now I've got room type, private room, and shared room. And what I'm going to do next is mostly look at the coefficients here. So I'm going to make a plot of this, ggplot on my x-axis, let's say neighborhood, sorry. And on the y-axis, let's give it the estimate, and I'm going to do geom point, and just for good measure, I'm going to facet wrap everything against the term. So I'm doing a lot of stuff in this code chunk, and realistically, maybe I want to break this up into a couple of things. That looks awful. I need to do the usual. I got to do the same thing. ggplot rotate axis labels, and there it is, right at the beginning. It's always right at the top, and ops. This is the one I copied. Okay, so let me copy this over. Same as always. take a look again. That's a little bit better. I think that angle isn't so nice. I mean, I'm turning my head too hard. So, all right, so what I'm looking at here is among private rooms, I'm going to zoom in even. This is still kind of hard to read. If I am comparing an entire home to a private room in Battery Park City, keeping stars fixed, that's going to save me about $120 in Battery Park City, $120 in Chinatown. It's going to save me a lot of money here in, it looks like the financial district. So if you wanted to save a bunch of room, you could, or save a bunch of money, you could, you know, stay in the financial district. And over here, actually, there's a big chunk of price difference also. Looks like NoHo, Roosevelt Island, Soho Theater District. Like there are big differences comparing one room type to another room type in each of those neighborhoods in Manhattan. It looks like, I would have thought shared room would save you even substantially more money. And it looks like in one place, in NoHo, it looks like having a shared room is actually going to cost you quite a bit more. My guess is that there's only one shared room in that neighborhood, and you're getting sort of like a weird outlying effect as a result of that. So I'm not putting confidence intervals on any of these things, and I'm not doing a formal analysis that as to whether or not these things are actually different across neighborhoods. But this is giving me some way of fitting a bunch of models and then looking at coefficients across all of those different models. And that turns out to be a pretty helpful thing to have. And I think that is where we're going to end things for this. So we've actually, again, we've covered a fair bit of ground here in the sense that we started out by taking a data frame and fitting a model to it and looking at the results, and then understanding how R deals with factors and doing things like this. We talked about, for a single model, doing diagnostics and hypothesis tests, and I think all of that is important. And then here, we are as much as anything doing exploratory analysis using linear regression. And that exploratory analysis is to say, you might want to understand associations in subgroups, look at the effect of stars across different boroughs, and that's not going to be the same as doing a formal hypothesis test about whether or not there is a true interaction there, but it does give you some way of understanding what might be the same and what might be different across these subgroups. And then we took it even further and did this nesting across neighborhoods in Manhattan, and we're sort of at that point playing around with ggplot and trying to understand the results of things that come out of this. So that's a lot of ground to cover. Thanks for sticking with it. And we will build on some of this stuff when we start, especially the nesting stuff. We're going to build on that when we start looking at things like bootstrapping and cross-validation, which are important tools in the context of doing linear regression in a data science perspective. So I'm excited. I hope you're excited. And that's all for now. Thanks very much.